Welcome to the course on numerical linear algebra and application. Today we are going to learn 45th lecture. Let us quickly recall what we have done in the previous lecture. In the previous lecture, we have learned how Jacobi method, Gauss-Seidel iteration method and successive over relaxation method would be helpful in order to find out the best approximation in few iterations. In contrary to that, today we would like to learn some new concepts, how these methods would be applicable for realistic applications. The first and foremost example is simulating transient current for an electrical circuit. Given an electric circuit consisting of 4 loops, suppose we are interested in the transient behavior of the electric circuit. In particular, we want to know the oscillation of each loop with respect to other, which would be defined by so-called the Kirchhoff's voltage law. L is the inductor, I is the current, C is the capacitance, and T is with respect to time variable. So, you will have transient current for an electrical circuit. If you look at closely over here, you see this is the coil L1, this is the coil L2, this is the coil L3, this is the coil L4. This is capacitor C1, capacitor C2, capacitor C3, capacitor C4. The current flow is I1, I2, I3, I4 in the clockwise direction. So, second loop is minus of L2 di2 upon dt minus of 1 over C2 integral of minus infinity to t I2 minus I3 dt plus 1 over C1 times of integral of minus infinity to t I1 minus I2 dt. So, loop 3 is minus of L3 di3 by dt minus 1 over 3 integral minus infinity to t I3 minus I4 dt plus 1 over C2 integral of minus infinity to t I2 minus I3 dt. So, in the loop 4, you will have minus of L4 di4 by dt minus 1 by C4 integral minus infinity to t I4 dt minus 1 over 3 integral of minus 1 infinity to t I3 minus I4 dt. The system of ordinary differential equations given above can be differentiated and rearranged as L1 times of d square I2 upon dt square plus 1 over C1 times of I1 minus I2 will be equivalent to 0. Second is L2 times of d square I2 upon dt square plus 1 over C2 times of I2 minus I3 minus 1 over C1 times of I1 minus I2 is equal to 0. And third one is L3 d2 I3 upon d2 plus 1 over 3 C3 I3 minus I4 minus 1 over C2 I2 minus I3 will be equivalent to 0, which we can write it as L4 times of d2 I4 upon dt2 plus 1 by C4 I4 minus 1 over C3 I3 minus I4. So, the differential equation will define the changes in the current with respect to time, where C is the capacitance. Assuming that Ij is Aj times of sine of omega t, that is J is equal to 1 to 4. So, from 1 we can have minus of L1 times of A1 omega square sine of omega t plus 1 over C1 times of A1 sine of omega t minus 1 over C1 times of A2 times of sine of omega times of t is equal to 0. So, which can be written as 1 over C1 minus L1 omega square A1 minus 1 over C1 A2 is equal to 0. Similarly, from 2 to 5, we obtain respectively the following equations. So, in this case, minus 1 over C1 times of A1 plus 1 over C1 plus 1 over C2 minus L2 omega 2 multiplied with A2 minus 1 over C2 times of A3 is equal to 0, minus 1 over C2 A2 plus 1 over C2 plus 1 over C3 minus of L3 omega square times of A3 minus 1 over C3 F4 is equal to 0, and third one is minus 1 over C3 A3 plus 1 over C3 plus 1 over C4 minus L4 omega square times of A4 is equal to 0. So, the above is an eigenvalue problem. To see it is more clearly, let us consider the special case. That is C1 is equal to C2 is equal to C3 etc. is C, and L1 is equal to L2 is equal to L3 is equal to L4 is equal to L. Assuming lambda is equal to LC times of omega square, and noting that Ij is equal to Aj times of sine of omega t, j is equal to 1 to 4, we obtain the following eigenvalue problem. So, you will have 1 minus 1 0 0 minus 1 2 1 minus 1 7 0 0 0 1 2 minus 1 0 0 minus 1 2 multiplied with I1 I2 I3 I4 will be equivalent to lambda times of I1 I2 I3 I4. So, there is an error over here, I3 and this is I4. Similarly, I3 and this is I4. So, the solution of this eigenvalue problem will be given us the natural frequencies, that is omega I square is lambda I upon LC. Moreover, the knowledge of the eigenvectors can be used to study the circuit's physical behavior and such as the natural mode of oscillations. These eigenvalues and the corresponding normalized eigenvectors, that is lambda 1 is equal to minus of 1.26, lambda 2 is equal to 1, lambda 3 is equal to 2.3473 and lambda 4 is equal to 3.5321. So, we can write as corresponding this each lambda, this is the one eigenvector and this is another eigenvector, this is the third eigenvector and this is the fourth eigenvector. Now, from the directions of the eigenvectors, we conclude that for lambda 1, all the loops oscillate in the same direction. For lambda 3, the second and third loops oscillate in the opposite direction. From the first and fourth and so on and so forth. Now, we can see an example of statistics, that is principal component analysis. Many practical life applications involving statistical analysis, that is stock market, weather prediction, involves a huge amount of data. The volume of and complexity of the data in these cases can be the computations required for analysis practical problems infeasible. So, in order to handle and analyze such a voluminous amount of data in practice, it is therefore necessary to consider the data problem. The basic idea will then be chosen judiciously as K. So, the components K from data set containing n measurements on P, that is P is greater than or equal to K, original variables such as much of the information, if not in the original P variables, is contained in the K chosen components. Such K components are, which we call it as principal components of the statistical data. So, you see from this figure, so this is, that is wavelength 0.1206, So lambda 2 is 1, lambda 3 is 1, lambda 4 is 3.5321 and lambda 3 is 2.3473. Look at this. This is the coil and this is the inductor and this is the current. The knowledge of eigenvalues and eigenvectors of the covariance matrix is needed to find out these practical applications. Although specifically if omega is the corresponding to the random vector x, that is x is equal to x1, x2, xn, lambda 1 greater than lambda 2 greater than lambda 3 like this. These methods are the components corresponding to the eigenvalues and we can write it as omega I is equal to xi transpose x, for I is equal to 1 to p. Furthermore, the proportion of the total population variance due to this is given by this expression. Note that the covariance matrix is symmetric positive definite matrix and therefore its eigenvalues are all non-negative. If the first k ratios constitute the most of the total population surveys, then we show that the matrix is the largest. The matrix K is the largest component used in installed analysis. And by knowing the eigenvalues, we can able to find out some good spectrum which does not need to be computed. To this end, we remark that many real life practical situations such as index or the Darcy's law, industrial average can now be better understood and explained to the principal component analysis, and this is shown in the example. So if you look at this market example, Johnson and Richardson 1992, suppose that the covariance matrix for the weekly rates of research, weekly rates of return for stocks of the 5 major companies, we detail in the like this. R is equal to, first element is 1000, second element is 0.577, third element is 3.877, fourth element is 0.462. So in the eighth, the last one is 0.462, 0.1322, 0.426, 0.526 and that is 1.00. The first two eigenvalues of R are lambda 1 2.857 and lambda 2 is equal to 0.809. The proportion of total population variance due to the first component is approximately, that is 57%. The proportion of total population variance due to the second component is 16%. Thus, the first two principal components account around 73% or the total population variance. Therefore, the eigenvalues are corresponding to these principal components are x1 transpose is 0.464, 0.2447, 0.470, 0.421, 0.421 and tilde will be, and x2 would be 0.240, 0.2509, 0.260 minus of 0.526 minus of 0.582. So these eigenvalues have intersecting interpretations from the expression of x1. We see that the first component is equally weighted sum of the 5 stock exchange literature. This component is generally called the market component. However, the expression for x2 tells us that the second component represents a contrast between the chemicals of juice and oil industry stocks. This component will be generally called an industry component. So this is called as industry component. Thus we conclude that about some 57% of total variation in these stocks return is due to the many activities and 16% of due to industry institute interactions, or we can call it as academic activities. The eigenvalue problem also arises in many other important statistical applications. For example, when you are computing the canonical representation of the forms. So it's a final component, more eigenvalue problems arising in statistics, such as in the principal component analysis and canonical relations, are actually SVD problems and should be handled computationally using singular value decomposition. Localization of eigenvalues. As we have seen just in several practical applications, explicit knowledge of eigenvalues is not required. All that is required is to acknowledge of the eigenvalues in a space, some given works of the complex plane or estimates of some specific eigenvalues. There are ways such information may be acquired without actually by computing the eigenvalues of the matrix. We start with a well-known matrix known as Gershgorian theorem, which already we did it. So what is the Gershgorian theorem tells us that? The Gershgorian tells that let A be a square matrix. We define a matrix Ri summation j is equal to 1 to n aij, that is I is not equal to 1. So the each eigenvalue lambda I of iai satisfies at least one of the following criteria. This is the criteria, that is mod of lambda minus aii less than or equal to Ri. So in other words, all the eigenvalues of A can be found in the union of the disk, that is Z such that Z minus aii less than or equal to Ri. So the proof is very simple, but still we will try to prove it in a couple of minutes. Let lambda be an eigenvalue of A and 10 power and beta be an integrated value, normally 10 power minus 6. So then Ax is equal to lambda x can be written as A minus lambda I is equal to this thing, I is equal to n aij xj. So this ai is not equal to x of j. So where xi is the component of the vector x, let x be the largest component of x. Then since xj upon xk will be equal to 1, from the above we can write it as 1, that is norm of, that is modulus of lambda minus ai is equal to less than or equal to summation j is equal to 1 to n mod of jij mod of akj xj xk is less than or equal to j is equal to 1 to n, ij is not equal to k, theta k. Lambda is contained in the open disk. So computing selected eigenvalues and eigenvectors, we have just seen that in several applications all one needs to compute is a few largest or smallest eigenvalues and the corresponding eigenvectors. Examples of such includes the buckling problem. It is the smallest eigenvalue that is in the most important of life. So that is the buckling problem. Second one is vibration analysis of characteristic structures. A common engineering approach would be available. A common engineering practice in vibration engineering is to compute just the first few smallest estimated values and the corresponding eigenvectors. So because it has been seen in some practice that the larger eigenvalues and eigenvectors contribute very little to the total response of the force, the same remarks also hold in the case of HODs of conveying others, modeled by a system of second order differential equations arising in the finite element method and reduces into what you call algebraic equations. Similarly, we can find out some statistical applications. In statistical applications such as those arising in principal component analysis, only the first few largest eigenvalues need to be computed. There are other applications where only the dominant eigenvalue and the subdominant eigenvalues and the corresponding eigenvalues are required. So in today's lecture, what we learned is, we learned about the new methods, how the acceleration criteria takes place for realistic examples. Thank you very much for listening to my lecture today. Thank you once again.